Welcome you all. Myself, Dr. N.R. Devi, Assistant Professor, Department of Physics, Auxilium College, Vellore. In this session, we are going to learn about optical fiber communication. Now, we are going to see about introduction about optical fiber communication and optical fiber. Fiber optic communication is a method of transmitting information from one place to another by sending pulses of infrared light through an optical fiber. The light is a form of carrier wave that is modulated to carry information. Soon after the discovery of lasers, some experiments were carried out on propagation of information through light waves in open atmosphere. A light beam acting as a carrier wave is capable of carrying more information than radio waves and microwaves because of its high frequency. Due to atmospheric conditions like rain, fog, etc., the efficient communication is disturbed. Hence, to have an efficient communication system, the light which carries the information requires a guiding media known as optical fibers. Thus, fiber optics, it is branch of optics which deals with the transmission and the reception of light waves using optical fibers which acts as a guiding media. A communication system that uses light as the carrier of information from a source to a destination through a guided fiber cable made up of glass or plastic is called an optical fiber communication system. The information carrying capacity of a communication system is directly proportional to its bandwidth. The wider the bandwidth, the greater is its information carrying capacity. Light frequencies used in fiber optic systems are between 10 power 4 and 4 into 10 power 14 Hz. As a result, they have higher information carrying capacity. Optical fiber. A fiber optic cable, also known as an optical fiber cable, is an assembly similar to an electrical cable but containing one or more optical fibers that are used to carry light. The optical fiber elements are typically individually coated with plastic layers and contained in a protective tube suitable for the environment where the cable is used. Core and a cladding layer selected for total internal reflection due to the difference in the refractive index between the two. An optical fiber consists of a central core glass surrounded by a cladding which is of slightly lower refractive index than core. It is made up of transparent dielectrics SiO2, glass or plastics. In practical fibers, the cladding is usually coated with a layer of acrylate polymer or polyimide. This coating protects the fiber from damage but does not contribute optical waveguide properties. Individual coated fibers or fibers formed into ribbons or bundles then have a tough resin buffer layer or core tube extruded around them to form the cable core. Several layers of protective sheathing, depending on the application, are added to form the cable. The protective layer is used so as to make the optical cable to withstand for hard pulling, bending, sketching, rolling, etc. Optical fiber is light in weight, smaller in size, and is flexible so that it can bend to any position. It is non-conductive, non-radioactive, and non-inductive. It has high bandwidth and low loss and no internal noise crosstalks. The structure giving the optical fiber, we have core material is made up of silica, it is surrounded by cladding and it is surrounded by silicone coating, and then it is surrounded by buffer jacket and stent member and black polyurethane outer jacket. Principle and propagation of light in optical fiber. To consider the propagation of light within an optical fiber, utilizing the ray theory model, it is necessary to take account of the refractive index of the dielectric medium. The refractive index of a medium is defined as the ratio of the velocity of light in a vacuum to the velocity of light in the medium. Light rays travels more slowly in optically dense medium than in one that is less dense. When light travels into a different medium, the speed of the light changes and the light is refracted. When light travels from a denser medium, example glass, to a less dense medium, example air, the speed of the light increases and the light refracts away from the normal. The angle of refraction is greater than the angle of incidence. As the angle of incidence is increased, the angle of refraction also increases. At a certain angle of incidence, the light will refract at 90 degrees and travel along the boundary between the two media. This angle of incidence is called the critical angle. If the angle of incidence is increased further so that it is greater than the critical angle, the light will be totally internally reflected. The conditions required for total internal reflection to occur are: the light must be traveling from a more dense medium into a less dense medium, example from glass to air. The angle of incidence must be greater than the critical angle. The diagram shows the light refracting from glass into air, where the angle of refraction pi 2 is greater than the angle of incidence pi 1. The diagram shows light hitting the glass air boundary at an angle that is equal to the critical angle, that is pi I is equal to pi c. The diagram shows the light hitting the glass air boundary at an angle that is greater than the critical angle, that is pi I is greater than the pi c. This is the mechanism by which light at a sufficiently shallow angle may be considered to propagate down an optical fiber with low loss. The ray has an angle of incidence pi at the interface which is greater than the critical angle and is reflected at the same angle to the normal. Light infrared getting in at one end undergoes repeated total internal reflection and emerges at the other end. Critical angle is calculated from Snell's law of refraction. Sin pi c is equal to n2 by n1. Acceptance angle and numerical aperture. It is useful to enlarge upon the geometric optics approach with reference to light rays entering the fiber. Since only rays with the incident angle greater than the critical angle at the core cladding interface are transmitted by total internal reflection. Acceptance angle. It is defined as the maximum angle to the axis at which the light ray may enter into the fiber in order to get propagated. Numerical aperture. The numerical aperture of a fiber is a measure of the light collecting ability of the fiber. The diagram shows the acceptance angle theta A when launching light into an optical fiber. The incidence angle within this conical off angle will be propagated through an optical fiber and it will be totally internally reflected. The numerical aperture will be calculated from sine of the acceptance angle, that is sine theta A is equal to root of n1 square minus n2 square. Types of optical fibers based on materials, modes and refractive indices. Based on optical fibers, material, number of modes, refractive index profile. It is classified depends upon the material it is made up of, that is glass fiber and plastic fiber. And it depends on number of modes. It is classified into single mode fiber and multi-mode fiber. and it depends on refractive index profile. It is classified into step index fiber, graded index fiber. In step index fiber, we have single mode step index fiber and a multi-mode step index fiber. In graded index fiber, we have only multi-mode graded index fiber. Based on materials in which the fibers made, it is classified into two types. Glass fibers, if the fibers are made up of mixture of metal oxides, silica glasses, it is made up by one of the following combinations of core and cladding. Core made up of SiO2, cladding P2O3 SiO2. Core GeO2 SiO2 and cladding SiO2. Plastic fibers. If the fibers are made up of plastics which can be handled without any care due to its toughness and durability. It is made up by any one of the following combinations of core and cladding. Core polymethyl methacrylate, cladding copolymer. Core polystyrene, cladding methyl methacrylate. Modes of propagation. Mode is one which describes the nature of propagation of electromagnetic waves in a waveguide. Light propagates as electromagnetic waves through an optical fiber. All waves having any directions above the critical angle will be trapped within the fiber due to total internal reflection. However, all such waves do not propagate through the fiber. Only certain ray directions are allowed to propagate. The allowed directions corresponding to the modes of the fiber. Modes can be visualized as the possible number of paths of light in an optical fiber. The paths are all zigzag paths excepting the axial direction. According, light rays traveling through a fiber are classified as axial rays or zigzag rays or skew rays. As the ray gets repeatedly reflected at the walls of the fiber, phase shift occurs. Waves traveling along the certain zigzag paths will be in phase and intensify. Waves traveling along certain other paths will be out of phase and diminish due to destructive interference. The light rays path along which the waves are in phase inside the fiber are called modes. Based on the modes of propagation, the fibers are classified into two types, single mode fibers and multi-mode fibers. Single mode fibers. It has very small core diameter so that it can allow only one mode of propagation. The cladding diameter must be very large compared to core diameter, made up of from doped silica and always be step index. Because of high bandwidth, they are used in long-haul communication systems. Multimode fiber. The multimode fibers are useful in manufacturing both for step index and graded index fibers. The multimode fibers are made by multi-component glass compounds such as glass, clad glass, silica, glad silica, doped silica, etc. Here, the core diameter is very large compared to single mode fibers, so that it can allow many modes to propagate through it, and hence called as multimode fibers. The cladding diameter is also larger than the diameter of the single mode fibers. Fibers, because of its less bandwidth, it is very useful in short haul communication.